All right, guys, so let's see. Last time we ended with this example of using these comparison tests. This is from section 10.3. I just have one last little thing to finish off in this section. But let me remind you of that example that we ended with. So recall that we were looking at the sequence of 1 over square root n squared plus 1. We showed it diverges. But the way that we had to show this, we had to compare it. We compared it to the sequence 1 over, or the series 1 over n plus 1. And it was a little bit tricky to do so. You might not have even known to do that in the first place, but what I sort of wanted to impress upon you was the intuition of looking at this, this term of this series and realizing that it pretty much looked like 1 over n. So that should be the series in the back of your mind that you want to compare this to. And now let me show you a better way to do it, easier, more powerful method. So that's the last theorem, the last limit comparison technique of this section. And it is called the limit comparison test. So, all right, let's say we've got we have two series of positive terms. AN and BN are both positive. And what we do is we take the limit of their ratio. So let L be the limit of AN over BN. And there's three possibilities. Well, first, I'm assuming that this limit exists and could also be infinity. So assuming that this limit exists, there are three possibilities. It's just some number, a positive number, in which case the series, sum of the AN terms and the sum of the BN terms, are both kind of more or less comparable in that the convergence of one totally determines the convergence of the other. So they either both converge or they both diverge. Let's see, if L is 0, so since L was the limit of the ratio of these two guys, AN and BN, L being 0 would be the situation where BN is a lot bigger than AN. So that means that doesn't necessarily tell us very much about AN, but if AN blows up, then so does BN. Finally, if that limit of that ratio is infinite, so let's see, this ratio being infinite, that corresponds to where the number on the top is the much bigger number. So, that means an is kind of dominating bn. So if L is infinity, then an converges implies bn converges. So let's see an example of this theorem in action. In fact, let's apply it to the example that we were already doing, which is this guy. And let's do it by comparing it to the term that we kind of expect it to be comparable to, which was 1 over n. Okay, so what the limit comparison test says you're supposed to do is take the ratio of the term you're comparing it to, of the sequence you're comparing it to, which in this case is 1 over n. So we're going to take the ratio here. You can think of this is like your bn, and this is like your an. So then an over bn is, okay, 1 over the square root of n squared plus 1 divided by 1 over n. Or let's see, let's rearrange this a little bit. This is n over the square root of n squared plus 1. And I want to take this limit as n goes to infinity. So let's see if you guys remember how to do this. Maybe you've done enough of them that you can tell just by looking at it, but I'm going to show the full detail. The way you would probably do this, at least at first, is like divide top and bottom by n. And let's see, we get 1 over, and when I move this underneath the square root sign, it becomes 1 over 1 plus 1 over n squared. Now it's kind of obvious what happens when you take the limit as n goes to infinity. So letting n go to infinity, this term right here goes away, and we just get 1. Okay, so what is the conclusion then of the limit comparison test? I took the ratio of the two terms, I got 1. Which of the 3 possibilities does this correspond to? Right, you can either get 0, infinity, or some number in between. This is the case you get 0. This is the case you get infinity, and then the first one is just, well, any other positive number. In this case, I got 1. So we are in the first situation, which is kind of the best one. Usually, you use the first condition, which is that is the two series are comparable. Their behavior is the same. What one of them does, the other one does. So since we got some positive non-zero number for that limit, namely 1, we can apply the first condition, which tells us that the two series are equivalent, at least their convergences are equivalent. So by the limit comparison test, 1 over root n squared plus 1 and 1 over n have the same behavior. Thus, since 1 over n diverges, so does 1 over root n squared plus 1. Now, the limit comparison test is probably the most powerful comparison test we've done. Yeah, Tara.
Is there any way you could draw the label for, I'm not understanding how if the limit is greater than 0, that automatically means that we can assume that either both converge.
Well, this example that I did was kind of meant to give you that sort of intuition, because notice what happened in this example. When I compared 1 over root n squared plus 1 to 1 over n, what really happened was that annoying little 1 went away. Because when n is a super huge number, if n is really big, the 1 doesn't really make much of a difference. And this is approximately equal to just 1 over n. So the limit comparison test says, yes, indeed, since those two, this sequence and this one, are approximately equal, at least for large n, their behavior is the same. Yeah?
So how come if L equals 0, which is a number, why does it diverge? And then infinity converge? Usually, I remember learning the opposite.
So, okay, let's see. If L is 0, let me make sure I did this right, because it's kind of confusing. So let me double check. If L is 0, that means that that means that Bn blows up much faster than An. So, in other words, Bn is dominated by An. That means that if An diverges, then Bn diverges. So recall the old comparison test, which was, I think it was just called the comparison test for series. So it said if you have 0 less than or equal to An less than or equal to Bn, and An diverges, then so does Bn. And the other way, the converse, said that, on the other hand, if this one converges, then so does this one. So let me check that that's what I wrote for the infinite case. So in the infinite case, if the limit is infinity, that means An is the bigger series. So if the bigger series converges, then the smaller series converges.
Yes. Is that also for the opposite? So An converges?
No. Yeah, that's where you cannot apply it. Okay. So, like I said, this is one of our more powerful limit tests. Let's try applying it to another problem. Okay, look, so I just applied it to a problem that we already knew how to do. Here's another example where off the top of my head, I wouldn't necessarily know how to do this any other way. So how about, let's investigate the convergence of, okay, let's see if I can remember this one. 1 minus, I think it was 2 to the negative 1 over n. Yeah, kind of a weird series there. But I want to point out, like, first thing to notice, it definitely will not converge if the terms don't go to 0. So let's just check that first. So if we let n tend to infinity, okay, You got to kind of keep track of this. N goes to infinity, so 1 over n goes to 0. So this goes to 2 to the 0, which is 1, and then it's 1 minus 1, which is 0. Okay, good. So that we can at least there's a chance that this might converge, because the terms do in fact go to 0. Now, what are we going to compare it to, though? That's kind of the tricky part. I don't know if I would know, actually. This is a problem in the book, and it tells you what to compare it to. Or it gives you a hint, a suggestion. Any idea, any guess? I wonder if any of you guys would know. I wouldn't know off the top of my head. And there might actually be more than one right answer, but the suggestion is to compare it to 1 over n. So you'll see, like this, the harmonic series just keeps coming back time and time again. It's a very sort of iconic example. Or what's the archetypal example? Is that correct use of the word archetype? I don't know what archetype means, but it's a very useful example. Okay, so let's take the limit of the ratio of those two series. We want the limit of the ratio of 1 minus 2 to the negative 1 over n compared with 1 over n. Okay. What does the top go to when n goes to infinity? 0. We already checked that. What does the bottom go to when n goes to infinity? Bottom, oh yeah, so n goes to infinity, the bottom goes to 0. So what's the word you guys are all thinking of now that we... L'Hopital, yeah. Okay, so this is now a situation for L'Hopital. So the top goes to 0, the bottom goes to 0. L'Hopital time. So I feel kind of weird using L'Hopital with n's. How about let me just do it with x's? All right, so it's like if it's 1 minus 2 to the negative 1 over x and 1 over x. If this is like my f and my g, let's see. We got to take the derivative of the top and the bottom. We're looking at the limit as x goes to infinity of this. So that's going to be the same as the limit as x goes to infinity of. All right, the bottom is easy enough. That's negative 1 over x squared, all right, because that's the derivative of 1 over x. Anyone know how you take the derivative of this guy? I had to double check this. I don't have it memorized. Yeah, so I mean, it's like, what's the derivative of, say, 2 to the x? Anyone know what d dx of 2 to the x is? Yeah, ln2 times 2 to the x. Okay, so this one, in fact, goes to negative ln2 times 2 to the negative x times negative positive 1 over x squared, actually. And let's see, we get to cancel out the x squareds. So this is just negative limit as x goes to infinity of ln2 times 2 to the negative 1 over x. As x goes to infinity, this exponent goes to 0, so this goes to 1. So we just get, am I missing a minus sign somewhere? Oh, this one, oops, yeah. There we go. Yeah, these minuses cancel each other out. Good. Did not expect a negative answer. So we just get ln2, which puts us once again in the situation, I actually just erased it, but that's the first possibility for the limit comparison test, a positive finite number. So our series diverges because the harmonic series diverges. Because the limit comparison test says they have the same behavior. Okay. Now, let's see. I don't have that much new material to do today, so I'm going to have a bit more time for examples than I usually do. One example, I thought it would be pretty cool to do in class, although we're not going to have time, but I gave it to you guys as an extra credit problem that you can submit on Gradescope. It's the book one. I don't know if you guys have seen this. Okay, check this out. This is a neat thing that you guys can go ahead and prove. I brought in a demonstration. It's a bunch of books. Okay. So, you guys have some questions on this? Any questions on this so far? Yeah?
How can you say 1 over n diverges, but we figured out, maybe I just messed up my question.
Oh.
We figured out the whole thing converged?
The limit of their ratio converged. We got ln2. So the limit comparison test says, okay, that's the situation where these two series are comparable, meaning they do the same thing. They either both diverge or both converge.
So if they both diverge, does that mean the ratio will converge?
The ratio, yeah, converged to ln2, which is a positive number. Right, it's like the limit comparison test, I already erased most of it, but whenever you get a positive number for the limit, that means the two series do the same thing. The other two cases were where you either get 0 or infinity. We usually don't use those. I just had to put that up there kind of for completeness. But if you can just get that their ratio gives you some positive number, then the two series do the same thing. So we got a positive number for the ratio, so the two series have to do the same thing. Sorry?
How do you know the same thing with diverging, not converging?
Well, because we already know that this one diverges. That was an example which I showed you. This is like our most famous diverging series, the harmonic series. We come back to this example a lot. I was able to originally prove that this guy diverged using the integral test. So yeah, it's we're gonna come back to this one even a couple more times today. The fact that if you remember, this is called the harmonic series, and the fact that it diverges.
Really quickly, are you screwed if you don't know if either of them diverge or converge, or because you have to know, right?
Yeah, you need to know one of them. Yeah, you need to know one of them. So let's say I want to do like a cool trick by stacking these books, okay? And I want to see if I can stack one book on the edge of the other, on the edge of another, the edge of the other, and see how far like I can get this stack of books leaning off the table. Like, how far you guys think I could go? That's getting kind of... Oh, so maybe you can tell this last book, it's not even over the table. This last book, Flatland, is completely off of the table. The edge of it lines up right here, which is past the edge of the table, which is right here. So I don't know if you realize that that was possible. It looks kind of crazy, right? And we can actually prove, using infinite series, that you can do this and more. I could keep stacking books all the way to the edge of the room. And in fact, all the way to the edge of the universe. You can prove this. You can prove that you can stack books on top of each other, and you need to get them really close to each other on this end so that the center of mass stays aligned with this side of the table. But if you stack enough books, you can still have them extending out infinitely far, but you have so many that are still like balanced on the side of the table that the center of mass still stays on the table right here. So you guys can prove that. I remember I first heard that in a physics class. I was like, what? No way. And then they proved it, and I was like, huh. All right, well, now it came up. I just noticed it was a problem in our math textbook, so I'll let you guys prove that one. That's one of the extra credit problems I gave. It was, I forget what problem number it was, but it's on Gradescope right now. So, okay, that does it pretty good for 10.3. 10.4 is kind of short, so let me try and knock this out right now. Okay, so let's start off with a definition. Let's say I have a series. So this is more on series, by the way. Okay, so let me say of series. These are all about series. But in the last section, we were only talking about positive. That is no longer the case. So this can be positive or negative, in which case, so we say that a series converges absolutely if the series where all the terms are positive converges. In other words, the series of absolute values converges. So, for example, how about 1 minus 1/4 plus 1/9 minus 1/16? It's the sum of the squares, inverse squares, excuse me, but we're alternating. So we put a little -1 term there. So here, an, the nth term, is -1 to the n plus 1 over n squared. So if I wanted to ask you guys whether this series converged absolutely, we would look at the sum of the absolute values of the terms, which is just the sum of 1 over n squared, right? The negative sign goes away. Just 1 plus 1/4 plus 1/9, and so forth. So,
I'm just trying to visualize it.
yeah, we've talked about this series. Anyone remember what it is? We actually know what number this equals. It's pi squared over 6. But even if we didn't know that, we should still know that this converges by p-test, yeah. So thus, the original series, we say it converges absolutely. Okay, as another example, How about this one? 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. So this is, it's the sum of the reciprocal powers, but again with this like alternating factor. What do you guys think about this one? Does this one converge absolutely? Anyone? It does not. Because if you take the absolute value of every term, which basically just means get rid of all the minus signs, this is our well-known example of the harmonic series, which, as we've been discussing today and previously, diverges. So, in this case, the sum of the absolute values is 1 plus 1/2 plus 1/3 is the diverging harmonic series. So, in fact, that series that I wrote down has a special name. So let me give you a couple more definitions. But first, since that series sorry. So we have a name for that theory, for that series. It's related to the harmonic series, but because it keeps alternating in sign, we call it, well, the alternating harmonic series. Yeah, Quinn?
So how does -1 to the n plus 1 equal 1?
Uh,
How does that change to 1?
It's -1 to the n plus 1. All right, -1 to the n is it's equal to -1 when n is odd and +1 when n is even. So this is a factor that we put on a sequence to make it alternate every other term. It's what accounts for the minus here, but the plus here, but the minus here, but the plus here. So here's some definitions. If Bn is, say, a sequence of positive terms, then a sequence of the form -1 to the n times Bn is called alternating. Or sometimes they put n plus 1. It doesn't really matter. So let me just say n or n plus 1, either one. As long as it goes from plus to minus, we call it an alternating series. And as a specific example, the one that I was just doing over there, -1 to the n plus 1 over n, or 1 minus 1/2 plus 1/3 minus 1/4. This one has a special name, which I just told you, but let me write down, is called the alternating harmonic series. It's like the same as the alternating, it's the same as the harmonic series, except it's alternating, meaning plus, minus, plus, minus, plus, minus. And here's one more bit of terminology. So back to this example, actually, wait, I can't give you this bit of terminology just yet. So let's look at the alternating harmonic series a little bit more. I'm going to show you something that's going to lead into this new situation because, okay, like I already defined absolutely convergent. When series are absolutely convergent, that's good. We like those. Those series behave very well. But the alternating harmonic series is our example of a series that is not absolutely convergent. Does that mean it's convergent? So, one of the, like I just said, absolutely convergent series are really good because of the following theorem. An absolutely convergent series converges. If it's absolutely convergent, then it's convergent. So absolutely convergent is a stronger criterion than just convergence. But we wouldn't have this theorem if they were equivalent. So somewhere out there, there must be some series that aren't absolutely convergent, yet they still converge. Yeah, that's kind of crazy, right? I mean, those are weird series. Okay, they do strange things. They have strange behaviors. We have a name for those theories. A series that converges but does not converge absolutely is said to be conditionally convergent. So the first thing you guys should be asking yourself is, do conditionally convergent series even exist? Right? Like, you haven't seen any yet, as far as you know. Or have we? Well, okay, we wouldn't have a word for it if they didn't exist. So they must exist, and here's how I'm going to demonstrate that. By looking back, right, by looking at the alternating harmonic series a little bit more. So this guy, which is 1 minus 1/2 plus 1/3 minus 1/4, and so forth. Okay. Let's graph this guy. So 1, 2, 3. And let's say this is up at 1. So at 1, it's equal to 1. Now, 1 minus 1/2 is 1/2. So that brings us back down to about there. I'm plotting the partial sums, by the way. So the next one will be 1 minus 1/2 plus 1/3. So I now go up 1/3 from here. All right, I started by going up 1 and then down 1/2. Now I go up 1/3, which should be about right there. And now, wait, that's right about there. I'm going to go down 1/4, which is going to be right about there. And now go up 1/5. Now down 1/6. Oh, yeah, okay, so this series does display some nice properties, like it looks bounded. It does, in fact, it looks to be settling in at some number here. Like, I don't know if you can kind of tell, there's a line here that it looks like these values are getting closer and closer and closer to. So if you just looked at this graph, you would say, man, it looks like there's a limit. Even though this series does not converge absolutely, it looks like it still converges. And in fact, it does. So we have a theorem that tells us that it converges. And in fact, it even converges to a number I can tell you guys. I just can't prove it right now. But so this series converges to the number ln2. Strangely enough. Well, it's not that strange. We'll be able to prove this fact once we do Taylor series. For now, but the point is it converges. And there's a test that we have for exactly this type of situation. So this test is called the alternating series test. It's one of the only situations we have for determining the convergence of these weird, bad series that don't converge absolutely, but they still converge. And it only works for alternating series. Okay, so if Bn, it's a sequence of positive terms, but not only that, I need them to be decreasing. I need them to be getting smaller. I.e., B1 needs to be bigger than B2, needs to be bigger than B3, and so forth. Okay. So the terms are positive, they're decreasing. In this situation, we can say something about the convergence of the alternating series. So in this case, the alternating series, negative 1 to the n plus 1 times Bn converges. That's the result of the theorem. That's the statement. If you're alternating and your terms are getting smaller, then you converge. And the picture, so I'm not going to prove it, the picture should be the proof for you guys. It's not super rigorous, I know, but this is what it looks like every single time when you alternately add, then subtract, then add, then subtract, but you're adding and subtracting consecutively smaller and smaller numbers. In that case, you actually approach a specific limit. So the alternating harmonic series is the prototypical example of applying this test. So let's see. I'll give you some more examples, but I want to say something that's kind of neat and weird while I'm still on this, because when I gave you the definition, oh sorry, I should underline. Oh, I did underline. Okay, when I gave you the definition of conditionally convergent, I said these series are weird. The conditionally convergent ones are weird. It's kind of hard to figure out when they converge. We have this specific test for if they're alternating and decreasing, but in general, they're kind of tough. And there's a theorem that you learn in analysis. So this is beyond the scope of this class, but I'm just going to tell you guys as sort of an interesting factoid. If you rearrange, let me phrase it this way. It is possible to rearrange a conditionally convergent series to converge to any number you want. Yeah, it's kind of crazy. It's really bizarre. So I'm not going to get into that. That's a sort of real analysis issue thing, but it should just sort of give you an idea that these are kind of badly behaved series, and we're only sort of lucky enough that they just happen to converge, and it's really just an artifact of the way that they're written. But, so while we're on the topic, let me give you another one, which actually I gave you a really cool extra credit problem on. How about this one? 1 minus 1/3 plus 1/5 minus 1/7. Anyone know what this series converges to? I assign as an extra credit homework problem to show exactly what it converges to. Anyone know? This adds up to pi over 4. Another crazy series formula for pi. Right? Like, where do all these things keep coming from? How many formulas have we had for pi now? So here's another one. It's probably the easiest one we've had so far. It's just adding up the reciprocals of all the odd numbers and alternating. So I ask you to prove this in an extra credit problem. But what I just want to point out now, notice that this is, again, just the type of series that the alternating series test applies for, right? Like, you need to check two things. First, is it alternating? It is going, yeah, plus, minus, plus, minus, plus. It is alternating. Secondly, are the terms getting smaller and smaller? Yeah, they also are, yeah. 3rd, 5th, 7th, and so forth. So this is exactly when we can apply the alternating series test. Now, what if, as for another example, what about, say, like 1 minus 2 plus 3 minus 4 plus 5, and so forth? How about this series? We can do the alternating series test here. Oh, yeah. So this one does not converge. I encourage you to verify that. And we can, even though it is alternating, the terms are getting bigger, not smaller. So I encourage you to check that by computing the partial sums, that it diverges. And even though it alternates, the test doesn't apply because the terms are getting bigger. Okay, cool. And that wraps it up.